Hello everyone. Today we are going to take a look at section 11.2, which is on the conservation of kinetic energy, specifically in collisions. Alright, so we're going to be looking at two objects that are running into each other. So our learning target today is that energy can be transferred, that's something new, between objects. And the essential question we are trying to answer today is, how does the law of conservation of energy apply in collisions? Alright, so let's go ahead and start with a little bit of review and make sure we remember what the law of conservation of energy says. So, the law of conservation of energy right here. Remember, hopefully you're hearing this in your head, energy cannot be created or destroyed, good for you, but it can, change forms. Alright, and here's the new piece, or be transferred. So what that means is that we can't make new energy, we can't get rid of energy, we can change it from potential to kinetic, we can change it from kinetic to heat, or we can move it from one object to another. Now when that happens, you have to have work involved. So we're going to go down here, and we're also going to review quickly our work energy theorem. So remember, the work energy theorem says the work done on an object, it looks like abject, that's something different, on an object is equal to the change in energy of the object. And we are specifically today going to talk about kinetic energy. So if I were to write this as a formula, I would say the work, remember W is work, is equal to the change in kinetic energy, right? Ke is kinetic energy, and that should look familiar to you. We are also going to need to know the kinetic energy formula, 1/2 mv squared. Remember that work is in joules, kinetic energy is in joules, m is mass, that's in kilograms, v is velocity, that's in meters per second. Okay? Hopefully this is all coming back to you. So, let's take a look specifically then at an application of this. So remember our essential question, how does the law of conservation of energy apply in collisions? We're going to look at two different types of collisions today, and then we're going to focus on the second one. So an inelastic collision happens when two objects collide and stick together. When we looked at momentum way back when, before Christmas, this is what we looked at, right? Collisions where two objects collided and stuck together. So if I look at my objects here, I can see that I've got a blue box and a yellow box, and the blue box is moving to the right, the yellow box is moving to the left, they hit each other, they stick together, maybe there's Velcro or something in there, who knows, and they're moving off together, toward the right. Okay? So that's what's happening. And just as a quick reminder, remember that mass is going to remain constant. Right? Neither of these things are going to gain or lose mass because of this collision. So, let's go ahead and talk a little bit about direction, because I wrote us a little reminder up here. Direction is going to be important. So, if we look at the blue box, it's moving, so it has kinetic energy, and I'm going to define this as the positive direction. So my blue box has positive kinetic energy, because I'm going to say that that's moving in the positive direction. Now that means that my yellow box, which also is moving, and so it has kinetic energy, is going to have negative kinetic energy because it's moving in the negative direction. So what about after they've collided with each other? They're still moving, right? So they still have kinetic energy. What do you think? Is this going to be positive kinetic energy or negative kinetic energy? Good for you. This is positive kinetic energy because it's moving in a positive direction. All right? And the law of conservation of energy tells us the total energy here is conserved. So I take the positive energy of the blue box, the negative energy of the orange box, and I, after the collision, stick them together, so I've got the kinetic energy of the blue box plus the orange box, and this is also going to be positive because it's going in the positive direction. Everybody good with that? Okay, and just as a reminder, work is done during the collision. Right? Because remember that work is a force times a distance. So the blue box is exerting a force on the orange box, and it's moving in the distance or in the direction of the force, and so work was done. Okay? All right, so take a minute, stop the video if you need to. Think about that. All right, so let's go ahead and look at an elastic collision. Now, this is where we're going to put the majority of our energy here on this elastic collision. Oh, you know what? I don't want blue. One of the balls is blue. Let's do orange. Okay, so if we take a look at our elastic collision, what do you notice first is the difference between the elastic and the inelastic collision? Good for you. So lost my train of thought. In an elastic collision, the objects are going to hit each other, collide, right? And they're going to bounce off. So they do not stick together here. They're going to collide and they're going to bounce off. All right. So here we go. I have a blue, I don't know, it looks like a billiard ball maybe, or a pool ball, and a purple pool ball. So let's think about the direction about this again, okay? So is the blue ball positive or negative before the collision? Good. This has positive kinetic energy. How about the purple ball? Yep, this one has negative kinetic energy, right? It's all about direction. Now, if you want to switch those directions, positive and negative, you could, but I'm going to leave it like this. Okay, what happens when they hit each other? Well, this is where work happens. Right? There's a force. The balls are moving in a distance, in the direction of the force, of the greater force. And then what happens in this case after the collision? Well, the blue ball has changed directions. So this now has negative kinetic energy. What about the purple ball? Yep, it also has changed directions, and it's now going in the positive direction, so it has positive kinetic energy. All right, and just like before, we are going to remember that the mass remains constant, right? The mass is not changing. Okay, so let's do a little bit of analysis here. What's happening in this picture? Well, what we know is that the total energy is still conserved, even though they don't stick together. And so when we look at our equation, we're going to say, all right, well, the energy of the blue ball was positive, the energy of the purple ball was negative. They hit each other. The total energy isn't going to change. That's why we have an equal sign here. The total energy isn't going to change. But the blue ball now has negative kinetic energy, and the purple ball now has positive kinetic energy. Okay, because they've changed directions. All right, how do you feel about that? Okay. And what we know then is that the total energy, the total kinetic energy before this collision is going to be equal to the total kinetic energy after the collision. That's what the law of conservation of energy tells us. But we know that that total kinetic energy is split between the two balls. So we can say, well, that's weird. Where'd my box go? Let's try again. There it is. So we could rewrite this, and we could say the kinetic energy before of the first object, whatever it is, a ball, a box, whatever, the kinetic energy of the other object, sorry, that should say before. Let me try again. So I've got two objects before this collision, and their kinetic energy before is going to be equal to the kinetic energy after the collision. Balls or boxes or whatever, cars, trains, whatever, right? Okay? The total kinetic energy before is equal to the total kinetic energy after. And we can look at the whole system, or we could look at each object individually. All right. So let's do an example problem and see how this works. So here I have got a white ball that's moving, a red ball that's not moving. How do I know that? Well, because this says velocity 0, right? Okay, and then they are going to hit each other. That's why there's a before and after here. And then it looks like the white ball has stopped and the red ball is now moving. Okay, so let's see what the problem tells us. A moving ball, white, with a mass of 5 kilograms strikes a stationary red ball with a mass of 3 kilograms. So I've got a mass here of 5 kilograms. I've got a mass here of 3 kilograms. It does tell me that this ball is not moving. So I've got a velocity of 0. And the velocity, oh, that's a typo. This should say white. My bad. Velocity of the white ball is 1.5 meters per second before the collision. So my V1 or my V before is 1.5 meters per second. Okay? So, and is not moving after the collision. So we were right. This still has a mass of 5 kilograms. This still has a mass of 3 kilograms. This ball is now not moving, and this ball is moving. Let's see, we'll call this after. All right? But we don't know how much. Assume energy is conserved. Calculate the velocity of the red ball after the collision. So this is, in fact, what we're looking for right here. Okay, so what's this going to look like? Well, so I know that the kinetic energy, hang on, let me make this look a little bit better. I think we're going to need some space here. I know that the kinetic energy of the white ball plus the kinetic energy of the red ball before the collision is going to be equal to the kinetic energy of the white ball plus the kinetic energy of the red ball after the collision. Everybody good? Okay. So if I change this, instead of writing KE, I write 1/2 mv squared plus 1/2 mv squared, right? One's for the white ball and one's for the red ball, is equal to 1/2 mv squared plus 1/2 mv squared. And again, one's for the white ball and one's for the red ball. So let's go ahead and put some numbers in here. So I'm going to have 1/2 times 5 times 1.5 squared plus 1/2 times 3 times 0 squared is equal to 1/2 times 5, because the mass doesn't change, times 0 squared plus 1/2 times 3, and that's what I don't know right there, the velocity of the red ball after the collision. Now that was a lot of numbers we just plugged in, so if you need to stop the video and think about where all those numbers came from, make sure you do that. All right? So we're going to do some algebra here. 1/2 times 5 times 1.5 squared is going to give me 5.625. 1/2 times 3 times 0 is gone, so that's gone. And then I've got 1/2 times 5 times 0, so that's gone. I've got 1/2 times 3, which is 1.5 v squared. So all of a sudden it doesn't look so bad, right? Okay, so now what's the next step? We're going to divide both sides here by 1.5 because we'd like to get v by itself. And that is going to give me v squared of 3.75. And then if I take the square root of everything, that gives me v is 1.9 meters per second. Okay. Now, why is it moving faster than the ball was before? So let's go back up here. Right here, this ball is moving at 1.5 meters per second, but we just calculated that this ball is moving at 1.9 meters per second. How can that possibly be? Well, that's because the mass is less, right? So here's my mass, which is only 3, and here's my mass, which was 5. So because the ball is smaller, it has to be going faster in order to conserve the kinetic energy. All right? So if you need to go back and look through that again, please make sure that you stop the video and do that. And let's go on and look at example number 2. Now look at example number 2 is pretty complicated, right? There's lots of different steps here. So as we go through it, if you need to stop or listen to it again, make sure that you do. The your turn problem down here is going to be just like example number 2. So you're going to need to make sure that you pay attention. All right, here we go. 2 billiard balls each have a mass of 8 kilograms. All right, so here's my picture. And what I know is that the mass of A is 8 kilograms, and the mass of B is also 8 kilograms. And we know that's not going to change, so I can write it over here as well. All right, and if I look at this, I can see I'm going to have positive kinetic energy, negative kinetic energy, negative kinetic energy, positive kinetic energy, because they are changing direction. Okay, so that's important to keep in mind. Ball A is traveling to the right at 2.5 meters per second. Ball B is traveling left at 1.2 meters per second. So let's go ahead and put that in here as well. I know that I have a V here of 2.5 meters per second. And I've forgotten the other one. Oh yeah, 1.2. And this is going to be 1.2 meters per second. The balls collide and bounce off each other. Assume that energy is conserved. All right. So this says calculate the kinetic energy of ball A. All right. So the kinetic energy of A is going to be 1/2 mv squared. And this is going to be 1/2 times 8 times 2.5 squared. Put that in my calculator. I'm going to get 4 times 6.25, which gives me a kinetic energy of 25 joules. Okay. All right, part B says calculate the kinetic energy of ball B. Okay, so the kinetic energy of B is going to be 1/2 mv squared. But we do need to note that it's in an opposite direction, so we're going to call this negative. All right, so I should come out with a negative answer here. So kinetic energy of B is going to be 1/2 times 8 times 1.2 squared. Put that in my calculator. I'm going to get 4 times 1.44, which is going to give me 5.76, and so that means, we'll run out of room, the kinetic energy of B is negative 5.76 joules. Okay, and if you don't know why it's negative, you should figure that out because that's going to be important. It's positive because I've decided the right is to the positive direction and the left is the negative direction. So I have positive 25 joules for A since it's moving to the right, and I have negative 5.76 joules for B since it's moving to the left. Okay, after the collision, ball A has a velocity of 0.85 meters per second in the direction shown in the diagram. Remember, that's the negative direction. This is negative. Whoops. calculate the kinetic energy of ball A after the collision. Okay, so we know it's going to be negative. It's still 1/2 mv squared. So I've got 1/2 times 8 times 0.85 squared. And that's going to give me 4 times 0.722, which is 2.89 joules. And so I know that the kinetic energy of ball A after the collision is negative 2.89 joules. Okay. Using the law of conservation of energy, calculate the kinetic energy of ball B, after the collision. Okay, so now this is where we have to think. Law of conservation of energy. Kinetic energy of A plus the kinetic energy of B is equal to the kinetic energy of A plus the kinetic energy of B. And this side is before the collision, and this side is after the collision, right? All we've done is move that kinetic energy around. So this is going to be pretty straightforward because I've already done all of the kind of in-between calculations. So the kinetic energy of A before the collision was, maybe I'll write it over here, that'll be easier. Kinetic energy of A before the collision was 25 joules. Kinetic energy of B before the collision was negative 5.76. Kinetic energy of A after the collision is negative 2.89. Kinetic energy of B after the collision is what we're looking for. Right? Calculate the kinetic energy of ball B after the collision. So that's what we're looking for. Okay. So 25 plus negative 5.76 gives me 19.24. is equal to negative 2.89 plus the kinetic energy of B. If I add my 2.89 to both sides, then I am going to get a total kinetic energy of 22.13 joules. Why is it positive? Right? How come the final kinetic energy of ball B came out positive? Well, remember we said way up here at the top that because ball B is now moving to the right, the total kinetic energy should be positive, which is what it turned out to be. So that makes me happy. Okay, so your turn. You are going to do the same kind of problem that we just did with a red ball and a blue ball, ball 1 and ball 2. Okay, so the steps are the same. Look back at the example and you should be good. As always, if you have questions, we can talk about it during class the next time I see you. Thanks so much.